I want to continue. This is the third and final talk I'm going to give about STM here. And just like yesterday, first bit of a recap to see if you've missed anything, and then we'll get to it, all right? So STM is optimistic concurrency control. It operates on these things called TVARs, transactional variables. These operations are called STM transactions, and you can run transactions using atomically and combine them with or else. Transactions get rerun on conflicts, we know because of a log, and today we're actually going to see how that works. And you can call retry to rerun transactions yourself at a certain point. And the runtime reruns transactions after their inputs change. And you can use this for blocking operations in your transactions. All right, that was Monday, and yesterday we took STM TVARs as a building block for other things. So we can create TM vars in this way. You can create queues using two lists of TVARs, one for the read end and one for the write end. You can add counts for read and write capacity if you want a bounded queue. And we also saw how STM containers works and what problems it solves in order to avoid contention on hash map updates. All right, so that's what we did so far. And today, we're doing operational semantics of STM and discuss implementation nodes. So we're going to see how the runtime sort of works. And this is all work from other people. The main inspiration for this today was composable memory transactions, which is a 2005-2006 paper. I'm using the 2006 version. It's post-publicate. It has a correction. So, operational semantics of STM. Code is very nice and words are good, but sometimes we need to specify things precisely in order to get an idea of what is happening. And math and logic can help communicate clearly what's going on depending on what your definitions for clearly are. This works by putting things in a model, and a model can help us reason about what code or an implementation is doing. And where do models come from? Well, the authors create them. They come up with this language, or they use a language to communicate and specify what the code is doing. So a model is a communication tool. And in the end, it's just a communication tool. The implementation can differ from the model. In this instance, it actually does. But the model specifies the guarantees of the interface. Or the model doesn't cover everything in the implementation is a better way of specifying this, because the interface we'll discuss, and there will be some math, and the implementation has things that don't occur in the interface, like the logs. They aren't in the interface. Yeah, and some people try very hard to prove an implementation corresponds to a model. This isn't in the STM paper itself, so, but this is also something people try to do with models, except communication, they also try to verify correctness using them. And it's time for a bit of a confession. This is the first time I looked into operational semantics, and the math does look pretty scary, and I'm not sure if I get everything right. So it's a best effort attempt, and hopefully it's still interesting. Otherwise, I'll stand corrected and put it somewhere where you can see. So the question you might have is, like, why do you do this if you don't know what you're talking about, which is fair. But precisely because I don't exactly know what I'm talking about, this stuff can seem pretty intimidating, and it was to me, to be honest. And the STM paper is nice in the sense that it's very readable, and there's other ones which also use the kind of math that I'm going to talk about, or logic I'm going to talk about, which I have no idea about. But if this helps you, that you can take naive initial approaches at understanding intimidating stuff, that's a win in my book. So let's together see if this goes anywhere. So with that long disclaimer, apologies to the original authors, other people upon whose toes I'm stepping, and possibly you in this audience. Let's get to it.
By paper, you mean this one by Simon
Simon Peyton-Jones and Eric Meyer, and I'm forgetting people, but yeah, that one. All right. There's different kinds of semantics and different kinds of specifying what's going on in a program. The one we're looking at today is called small step operational semantics. There's other ones. I don't know the difference per se, but they apparently have different pros and cons. Ask someone who knows actually what's going on if you want to know more about that. But it looks like this. So the first thing I want you to see is that there's a lot of symbols. Right? We can establish that. The second thing I want you to know is that you asked for this. So let's see what's going on a bit further, right? And as another preface, this is from the paper, and that's about single-threaded Haskell. And here, the runtime repeatedly picks a thread, executes an I/O transition, and the program ends up in a new state. So a transition, which is a word here, is a way to move from one state to another state. And there are two types of transitions in that diagram I just showed you, but that went pretty quickly. But the important thing to know right now is there's two arrows, and an arrow means a transition. This arrow means an STM transition, so a transition in the STM monad. This one means an I/O transition, so a transition in the I/O monad. And if you read carefully right here, the runtime picks a thread, executes an I/O transition. That means that STM operations, they all get executed sequentially, which is different from what I promised you. I promised this like concurrent thing where things can happen at the same time. But I can only talk about this operational semantics thing if we're doing, because I copy stuff from the paper and because the paper is, is about single-threaded Haskell. So in this sense, it's about how to read these mathy things. And it's about getting some misconceptions you might have about the interface right.
So what we're trying to understand is how the double arrow converts to single arrow.
I'm sorry, could you repeat that?
Are we trying to understand this, that how the double arrow converts to the single arrow when we use atomically?
Yeah, so we can reason about the different steps that make up of STM transactions and what happens in case of exceptions and what happens in case of retries and or elses, and we get to specify that, but I don't get to like executes an I/O transition means and an STM. Multiple STM transitions, as we'll see in a bit, are part of a single I/O transition, which means that this doesn't say anything about the semantics of concurrent STM. But the guarantees are the same from what I've seen. So that might be disappointing, but it's what we've got. So, right. We also saw some stuff with bars instead of arrows, if you look carefully. And these are called rules of inference. And they work like this. You have premises at the top, then you have a bar, and then you have a conclusion. You might have seen this if you've done logic. And you can have multiple premises in logic, but we will only see rules with a single premise. And to be fair, I don't know if operational semantics means you can have multiple premises or not, but it's not important. Right, so this is readable, right? Like we've seen a surprising amount of this stuff, right? We've seen these two arrows, and we've seen this bar. So, victory, right? And I'm gonna, and this is the name of the rule, the stuff in the parents below. So let this sink in for a bit. Might seem intimidating. I'm gonna tell you about what I know. All right? So we've seen premise, conclusion. All right, let's dig into the premise. Yeah?
Sorry, could you repeat what the arrows mean?
Yeah, yeah, the arrows are important. This arrow means STM transition. This arrow means IO transition, right? And the star means 0 or more. This is one thing, and through 0 or more STM transitions, it ends up in another thing. If this is the case, then if this thing is true, and notice there's an M here and the M here, they mean the same M, then we end up here. So this says something about what happens in the STM stuff and how that corresponds to the IO stuff. With me so far? All right. So there's also a bunch of symbols here. You can read this M as a term, and a term is something the runtime knows how to execute. There's also a bunch of rules for that. You've seen and used a couple if you've done the exercises, like new tvar, or read tvar, or write tvar. And we'll see how those apply in a bit. This N, that's another term. Same deal. Pure is a keyword. It's like from the monad interface. Pure is like return, puts stuff in a context. So, and we're going to ignore this for a bit, right? So, given M, which occurs here, and given N, which occurs here, we can sort of see that this is about if M, through a series of 0 or more STM transitions, ends up with something that looks like pure N, then if we put the terms, or which can contain multiple consecutive terms, if we wrap those in an atomic, do a single IO transition, we end up with the same expression here. Right? With me so far? Good. The P's have something to do with the program state. It basically means you have this thing, it gets executed, and then this thing happens, and this is the transition. And the theta, it's the capital Greek letter theta, says something about the heap of our program. And the heap contains all allocations.
So it's the state, right?
It's the state, exactly. So, and the primes, accents, things mean a potentially different version of the heap in this case. And then we still have the delta to explain. The authors use the delta for the allocation effects of a STM transaction, which means creating new tvars, or which means creating new tvars. That's the allocation effect an STM transaction can have, right? So we start with the empty set, and we might do allocations. So
does this delta relate to the same state, or is the state of allocation to the state of thread different?
yeah, in this case, these are redundant. So these are also in here.
Okay, so
The allocations are on the.
So theta plus delta is theta prime, right?
Theta plus delta is theta prime. Not exactly, because we also can mutate things on the heap. We can change the contents of a t-var. That isn't counted as an allocation, it's counted as a mutation. All right, so again, and I'm talking about, I'm taking my time, I really want you to get this. Theta, heap, through one or multiple SCM transitions ends up in a different heap. So there might have been mutation, and how that works we'll see. There might have been mutation, and there might have been other t-vars that have been allocated. That's what this represents. And the heap also contains these allocations, and the reason the authors make a split between the heap and the allocations is because when we're going to look at exception handling, we might see that the allocations exist on the heap, but there's no pointers to them, but they end up being garbage collected. But we'll see. For now, there is this term or multiple STM terms. They get evaluated to pure n. Then the heap might have gotten changed. And then the heap also shows up here. Yes?
So why does the delta prime not show up on the bottom?
The delta prime does not show up on the bottom because if the transaction succeeds, which is the case we're discussing here, we end up at a pure thing, so the transaction succeeds. The allocations are also on the heap. So in a minute we'll see the rule where it's the next slide actually. So if you're okay with that, I'll skip to that and then we can see how it might be different. All right. So any other questions about this?
So in short, what is happening? Can you give a one-line summary of what happened?
An example?
No. Like how can you summarize this rule in one line?
The summary is if you have an STM transaction, it ends up with pure something, then the return value, the atomic M will evaluate to pure M and any mutations have occurred on the heap, and they get saved. Yeah.
So it's how STM transaction turns into IO transaction, right?
Yes. So once you execute atomically, you run an STM transaction, and if it succeeds, you get the value out of it. That's the summary. All right. Next slide. It's different, but it's sort of the same. Like I don't need to spend a lot of time doing the same symbols because they're actually similar. That's nice. We still have the atomic stuff. So if we do run an SCM transaction with a certain heap, and it doesn't succeed, it ends in a throw, an exception, then we might have a different heap. There might have been mutation to our t-vars, but that doesn't show up here. We keep the old one. But the allocation effects, which is creating new t-vars, if you do that in an SCM transaction, it doesn't matter if they stay on the heap. It doesn't matter because you can't reach them. I mean, it does mean that if you create a t-var in an SCM transaction and you throw it, you can get it out. But then you shouldn't do that.
So what is throw? What is throw?
Throw is exception handling in Haskell. So throw is like raise an exception.
So this is not pure functional error handling, it's actual error, right?
It's an error, yeah. So it's not like it's some Like it's an exception thing, like the runtime has.
But what kind of exceptions? You have exceptions in the IO monad, right?
You
Yeah,
can.
exceptions. Error is not recoverable, right? You cannot recover from.
You also have different kinds of exceptions. If you have a partial function, for example, you take the head of an empty list. That's a pure, like head is a pure function, but it can throw an exception.
But you cannot recover from that exception, right? You cannot catch it somewhere else.
You can if you want.
Catch the
You can.
partial function exception.
I think so.
But then when it ends up in IO.
Okay, it's an IO. It comes up as an IO exception. You cannot catch it as an IO.
I mean, like, you have to sort of be in IO to catch it, right?
Yeah, there's some rules about this, but like you can recover from that. So this bunch of symbols again, but it's sort of similar as the previous slide. We end up with a throw, then that will also be visible in I/O, and also only the allocation effects will have will stay on the heap. Good.
What does empty curly braces imply?
This is an empty set.
Okay.
So this means there haven't been any allocations, and then there have been allocations.
So this answers my question from your session about exceptions. So basically, if you have, in the presence of an exception, you may end up with side effects, allocations on the heap, but they're unreferenced, so it doesn't matter. That's the short answer.
Yeah, there in these semantics that I'm going to discuss, there is a slightly tricky thing still, but yeah. That's the post-publication correction, but I'm going to refer you to the paper if you want to read that. So we've learned and specified the heap can only be modified by an atomic block from SCM transactions.
So those are the only two inference rules? Those are the only two inference rules?
No, these are all the inference rules. But I'm going to discuss a subset. I'm not going to sit you through it. But we can discuss them later. So, so far we've learned, I'm going to discuss a few more, right? The heap can only be modified by an atomic block from STM, and exceptions propagate from STM and leave their allocation effects, like new TVARs, but no other modifications. And next up is how we read, create, and write TVARs. This time we're going to do without bars, so it's going to be easier even. But we do have an if statement. We're in STM again, as we can see with this arrow. If we read a TVAR, then it will take a single STM transition to go to pure, the lookup of the TVAR from our heap, if the TVAR is in our heap. Domain means is in the, is like this is a mapping, so it's in the part, the domain. Question, what happens if R is not in the domain of theta? Yes. Compiling fails. That's just an invalid program. We don't have that. So we don't need to specify it here. Good. Less rules, less math.
So this inference rule is available only when R belongs to domain of theta.
This inference rule is only available when?
R is in the domain of theta.
Yes, exactly. But for any compiling program, this is the case. Right, so this is the read rule. So we can use read TVAR and it will evaluate to whatever's on the heap for that TVAR. Cool. Write TVAR. This is where it gets interesting and we get to see some more symbols. Right? Single SCM transition. Original heap. Write TVAR to R, whatever is in M, ends up evaluating to pure unit. So it doesn't return anything, or it, yeah, you know what unit means. And then we create an extra mapping in theta in our heap from R to M. Again, if R is in the domain of theta. This is how we write stuff. This is what surprised me, basically. It's like, okay, it's a bunch of symbols, but you can actually read them, and I hope that I can sort of get that idea into you. So then we have another one, how we create new tvars, then we'll learn about the allocation effects. If we have new tvar M, and we get an R, remember new tvar returns a tvar. So this has type tvar. We store that into, and M is the original contents of the tvar. We store that in the heap, R points to M, and we allocate it as well. We record it as an allocation, which is redundant in the case of success, but which will stay on the heap in case of an exception, right? And that is only doable if R doesn't exist in the heap already. Cool.
Quick dumb question.
Yeah.
Just to make sure, R stands for reference, right?
Uh,
That's the thing?
yeah, it's a variable. It's
Okay,
a
so
reference.
Make sure I understand what
Yeah.
that is conceptually.
Yeah. Yeah, so it's the tvar itself, right?
Got it.
So another pit stop, we've seen creation, reading, and writing, and we've seen where the allocation effects came from. Namely, we recorded them here. And now we're going to see or else, and that one is a little more involved. And it has three cases. The first transaction succeeds, the first transaction throws an exception, and the first transaction retries. Why aren't there any cases for what the second transaction is doing? Well, those have already been handled by the previous rules. It's like, because it doesn't matter if something is in an or else or if it stands on its own. That's the second part. All right, so the first transaction succeeds. Transaction 1, transaction 2. Transaction 1 succeeds. You've seen this. And it ends up with a changed heap and changed allocations. Then we return the n here. And then we have the heap here. Oh, sorry, I think I got this arrow wrong. This should be a fat arrow. This should be an STM arrow, because we also record the allocations. Like the STM stuff needs to be inside an atomically block. So wrong arrow. Probably wrong in the next slides as well. So this is, everything's good. Yeah, let's proceed. So then it's this. In the case where the first thing throws an exception, we throw it again. Right? Wrong arrow again, sorry. So M1 ends up at a throw through 0 multiple steps, then we throw it. Wrong arrow, so this is in STM. This will all disappear because of the I/O transition I talked about previously. And last case, so that's this slide. Like, why is this a theta prime instead of theta? Aren't we handling exceptions? Well, it's because the heap modifications are still there. That's not a problem because the previous rule accounted for that, like to discard them. And then we have what happens in case of a retry. M1 resolves to a retry. Then we just evaluate M2 and see what happens. Again, wrong arrow. I'll correct it on the slides that I'll post online. Yeah, so that's what I wanted to cover, but there's something missing. We haven't seen a rule. Oh, yeah.
So
So a retry in M1 means don't retry M1, but instead retry M2 because of the or else?
Yes, exactly. That's the intended semantics. It's so you can, or else means run this. If it fails, run the second one. And fail here means the programmer calling retry. In the implementation part in a bit, we'll see that like this, if a thing fails because there's conflicts, it will get rerun in some shape or fashion. So it means do M2, okay? There's no explicit rule for what happens when retry is reached while we're in I/O. And that's sort of interesting. That's because the system doesn't make any progress when this happens. It blocks. Remember, we were talking about single-threaded Haskell. This is the rule that's just not here. So I'm not discussing this because the thread just hangs. There aren't any further transitions it can make.
I'm sorry. What do you mean by while in I/O?
Yeah. So with there is no single-lined arrow about what happens when a retry is reached and it bubbles up to the atomically block. Then there's no transition for what to do because the runtime just blocks the thread. Okay, cool. So other threads can make progress, and if any of the TVARs involved in a transaction changes, the thread can proceed. All right.
How do we model that?
Hmm?
How do we model the last line?
How do we, how this happens?
Yeah.
That's this part.
No, shouldn't we like specify that in the semantics?
No, because there isn't any way to make progress. So we omit the rule, and then there isn't any progress. There's no step to say, or there are no semantics for when there's no step. There are only semantics for when there are any steps to take.
No, but how do you say in the semantics that when this thing gets resolved, then the runtime unblocks this?
Yeah, then that's the problem I pointed out in the sort of introduction to this talk. The model doesn't cover everything. We haven't, this is like the contract to you as the programmer, but the implementation does some extra things. Namely, it keeps a log of access to your TVARs, and it keeps some other stuff we'll see. That isn't in the specification because there might be other valid implementations of this. And we don't put it in the semantics because it isn't part of the thing. The way we put this in the semantics is to say there isn't any way to make progress. And then, yeah. All right. Implementation. This is a bit more concrete than we've had all the math stuff. I hope the math stuff was nice. And hopefully it was less intimidating than it might have seemed. If that's the case, I call this a success. Let's do implementation. So I mentioned a log of access to TVARs a couple of times. And its purpose is to find conflicts before transactions commit. I haven't mentioned how it works, and that's this part. Each thread in this runtime has a log. It gets created as soon as a transaction starts. So this means the atomic block is, atomically is encountered. And each log contains a pointer to a parent. This may be null, so we can have nested transactions. That's important when we get to the or else bit. And it has a number of log entries. So yeah, that's for every SCM transactions. There is a log of things. So what's in the log entries? For every TVAR that a transaction has either read or written, there's an entry in this log. And these have three things: a pointer to the TVAR, its value when the transaction started, and its current value. This means that by writing to this log instead of writing to the shared structures, we can update values without modifying the actual memory of the stuff that other threads read from. How do we know there's conflicts, right? Assume we've written some stuff and we've done some stuff and we have a bunch of log entries. For a transaction, we look at all these log entries, and then we look at all the TVARs. And here we recorded the value of the TVAR when the transaction started. So if we're going to verify before we do a commit to see, we have the information to see if the TVAR changed during the transaction. This is linear in the amount of TVARs accessed. So commit the verify step, it takes more time depending on how many TVARs there were. Is it clear that we have enough information to detect conflicts based on this? The way this works is, I think, via pointer equality. And this, if you know bit of concurrency, might ring a few bells. Like there might be problems with this. I'll address those in just a moment. Yes?
When you say it's pointer equality, does this mean that if you read a TVAR, it's at value 5, and then some other thread adds 1, and then some other threads, and that finishes, so subtracts, some other thread subtracts 1, so it's again at 5. Would you still consider it the same?
Yeah, that's the ABA problem. Would you still consider it the same?
So you read it as 5, and you want to commit your
yes, in a very special case. No, yes in the general case. Sorry, yes in the general case. And the reason this is okay is because after we've read a TVAR, we won't read from the TVAR again. We read from this, its value when the transaction started. So through all the rest of the transaction, we use that value. So we don't. There is a guarantee that there aren't any intermediate steps that use the 6 instead of the 5. So aborting transactions, that happens when that can happen just by discarding its log. We haven't written anything to any other memory location accessible by any other thread. Writes happen to log in that third slot, right? So they don't have any effects. And reads also happen from the log. This is what I just talked about. This avoids the ABA problems.
So what is the ABA problem?
It's where it's an optimistic concurrency race condition where there's multiple things changing a value. And if you use optimistic concurrency of, if you use this way of see if anything changed, to detect a conflict, then you have a problem if the value changed during your transaction somewhere, and at the end, when you check for your changes, it's back again at the original value. Then you don't notice any conflicts, and then you let it go through while your transaction may have read another value in the meantime. But because we read from the log and not from the actual memory location, we only read once from the actual memory location, this is fine. All right, so this helps with the ABA problem. And yeah, committing is loop over the log. For each entry, write the new value to the TVAR. And in the single threaded runtime, this is enough. Like, only one thread can commit at the same time because there's only a single thread running. And we also specified that for a single I/O transition, that all the STM stuff happens in a single I/O transition. We just specified that a couple of slides back. And multi-core would need some sort of synchronization, or you'll have trouble when two threads commit to the same locations. But this is a similar problem you have in like databases and other stuff. So there would be some synchronization there, I think, but I'm not sure. Yeah.
Yeah, just to be sure, the committing transaction, you say like write all of them, but I presume like first you check if they're also valid.
Yes.
And after that you
Yeah.
start writing them.
Yes, exactly. Yeah. So once the transaction is almost finished, we first check it and then we commit it. Yeah, those are separate steps in the paper as well.
Like checking and writing is one atomic action.
Yes, that's one atomic action because it's a single thread at runtime, and I don't know how this works if we go multi-core. But this is a nice way to think about, like, sort of get a hint of how this works, right? One interesting side note is that there's cases where transactions can loop indefinitely because of the values they read. Like, for example, let's say you start off, you validate some logic, and then something changes, and now the logic is no longer valid. You reuse some values, and then you end up in an indefinite loop. This is something the author suggests. One of the how to fix this? Yeah. Well, I use the word obvious here, which is not really fair because I had never thought of it, but it's obvious in retrospect, right? And the fix is before you switch to a thread in a transaction, because transactions can block, right? This happens when something is waiting for different kinds of input. You run the check routine, and remember this works because it's a single threaded runtime. So if a transaction ended up in a retry and it's blocking and it's waiting, and stuff changes, then when the thing gets rerun, some assumptions might have changed or something, and then it might end up in an indefinite loop. That's something that can happen. So this is the fix. You don't.
Does STM maintains in the log how many times that is retried?
I don't think so.
Okay.
And I don't think you need it to implement any of this, but I might be wrong. So this is an interesting bit of knowledge, right? The thing that was most interesting to me is how to avoid buzzy waiting when you're in a retry. How do you know that that something changed? Do we, every time we commit, do we loop over all the threads and see if they have entries of this tvar in our log? No, we don't. That's the question, like, how does the runtime know that which threads need to rerun? Each tvar actually has a list of transactions which block on it. That's attached. So when another thread commits to a tvar, it can wake up any one of these waiting things. And this is how you, this is like the data structure they use to make this efficient. And these threads, when they wake up, they also need to, that's what I just talked about, they need to verify that their state is still, oh no, that they need to verify something, not sure exactly what they needed to verify. Never mind. Avoiding busy wait, it happens like this. That's the most important part, the way the pointers work. And then we have transaction nesting. Or else requires nesting of transactions. Any idea why? All right, I'll help.
Because or else transforms STM transaction to STM transaction. In order to have it transformed to IO transaction, it has to be in another transaction that's transformed the results to IO.
No, you cannot call or else on IO transaction or on IO actions.
That's why you need to have
yeah.
to have it inside another transaction.
Yeah, and another reason. So what you're saying is, if you you want to isolate execution of the alternatives is basically the point. So if you run the first transaction, it might make changes to the heap, and you don't want those to show up when you run the alternative. That's why you need nesting, or why the authors decided to implement nesting. So we can create a nested log. Remember the parent pointer? Well, that's how a nested log works. So we create a new log. It has a parent pointer to its parent, and a parent and a log with no parent pointer is the root. So if a nested transaction finishes, we validate its log and that of the parent, because and then we can merge. We need to validate that of the parent because the nested transaction might not have accessed all the TVARs that the parent has accessed, so we need to look at all of them. And then we merge them. How do we merge them? We just, I don't think that's here. How do we merge these logs? Everything that we've written and that the parent has also written, we update the write value, not the value that it was first read as. Then every new TVAR we've allocated in the nested transaction also ends up in the log of the parent, and that's it. Questions about this? All right. In the case of retry or else retry, and this is my last bit, I think, there is a question like which TVAR should we wait on before we retry a transaction? Well, the union of all those accessed in both transactions, because like the parent needs to eventually know all the stuff that has been accessed inside the entire thing, because a retry could propagate from the bottom somewhere and then end up at top level. If we're going to register the stuff, if we're going to get woken up for every variable that we've accessed, we need to do this union thing. And this is so that all of the TVARs which have been accessed can get the current thread ID on the waiting list. That's right. And this log is only used for installing these waiting entries, or it is discarded because both end up in a retry, right? If there's another or else, if that succeeds, then we're fine. That's the result of our STM transaction. If it retries, then and that goes up inductively, then these waiting entries can only be used for the notification bit, never for the actual commit bit, because it's a nested thing, right? So if we have a nested merged thing here and another nested thing here, and this succeeds, this is preferred. Yeah, I think that's it. As a summary, we've seen the operational semantics of STM, and we've discussed some implementation notes of how this could be done in a single-threaded runtime. It's not how the real thing works, but it might be a good didactic experience. I think it is. I hope the operational semantics part was interesting or at least enlightening, and if you are very good at that already, then there might not be much new. Hopefully it was interesting, this entire thing. All the slides are going to be online here. And feedback, feel free to tell me on today, or like anything else I've done, feel free to tell me or create a GitHub ticket or whatever you want. So thank you very much. That's all from me this summer school. I want to thank you for attending, the organizers for organizing, and I hope you have a nice rest of the week. Thank you.